I was talking about the ancient cultures, and the Arab culture really started in the year 622, the year of the hijrah, and the most famous historian of cryptography, David Kahn, wrote in his famous book, the Code Breakers. Anybody who's interested in the history of cryptography should start with that book. That is, it's over half a century old, but still the best general book about cryptography. It's also very well written. Dave is a journalist by profession, and he found that cryptology was born among the Arabs. They were the first to discover and write down the methods of cryptanalysis. And that is what I will talk about, or the first half of what I'll talk about. And you can recognize, for example, the English term cipher, like enciphering deciphering comes from the Arab word sifr, which means zero. And actually, in English, it used to mean zero as well, but it's now it means just a piece of coded text typically. Here are some names of cryptographers: al-Khalil, al-Kindī, Ibn Abdurrahim, al-Karkashandi, but I will only have the time to speak about one of them, al-Kindī, and I'll mention al-Khalil very briefly. Now, very little was known about Arab cryptology. In particular, when David Kahn wrote his book in 1967, or he wrote it before that, very little was known, and but in the last 2 or 3 decades, some cryptological writings were discovered in archives, mainly in Istanbul and elsewhere, I think. And there's a nice series of little booklets about the Arabic origins of cryptology by Rayati and others. And most of the early Arab work was unknown until these discoveries. So what I'll talk about, both in the crypto and in the math part of my talk, deals with the 3rd century after the hijrah. So that's the 9th century in the Christian reckoning. The caliph Harun al-Rashid founded in Baghdad the al-Ḥikmāh, the house of wisdom, that was originally a large library of works, but eventually under Ma'mun, it was open to general public, well, not general, to the public, and people came there to work and study, a bit like a university, except that most of the interaction was just one-on-one. So here is an old fictitious image, of course, of some of the scientists sitting together. They are in a group, but there was nothing like what we know as courses in today's universities. And at the Bayt al-Ḥikmāh, one of the big advances and tasks that they had was to translate scientific works from the earlier civilizations, like the Greek, Persian, Indian cultures, and they were translated there into Arabic. And had they not been translated into Arabic, they might have been lost forever. Many of the classical, for example, the Greek works, mathematical works, are only known via Arabic translations. They would have been lost otherwise. And eventually, they also reached the Western scientists. But as I said in the beginning, in the West, in Western Europe, science started much, much later, only around 1500 in the Renaissance. Now, one of the outstanding scholars here, or I think maybe the most outstanding scholar, was al-Kindī, Abū Yūsuf al-Kindī. So he lived in he worked in the 3rd century hijrah. And he's considered also in today's Muslim culture as the father of Muslim philosophy, and he worked on translations from the Greeks. He was a prolific author. He wrote many books, like over 100 books on medical and many other subjects. And what is of interest for us here and today is the first scientific study of cryptology. A major advance. Here are 3 fictitious images of al-Kindī, of course, because of the Quranic restrictions on representing human faces. No true image of al-Kindī exists, nor of the other people at that time. But here they are. This is a drawing, and these are 2 stems from Iraq and Syria. And his book is called Risālah fi istikhrāj al-mmah. Mmah is a secret, and I learned yesterday from the students here that it's related to blind. Is that correct? So blinded messages, and in English, the manuscript on deciphering encrypted messages, and that is truly the oldest existing book on cryptography. Now, al-Kindī at first followed sort of classical Arab philology, the study of linguistic methods like the distribution of consonants in Arabic. Linguistics always played a larger role, I would say, in the Arab culture than in other cultures, because of the importance of the Quran and because of the difficulty of reading Arabic. Because when you don't use the diacritical marks, then many words and many sentences can have multiple meanings. So it was always considered a necessity to read very carefully these texts, the holy texts, and among others to consider the distribution of consonants and so on in Arabic. He gave an impressive classification of the cryptographic methods of his time, and in an amazingly modern way. He talked about what we now call cribs, the search for probable words in encrypted messages. He introduced in a very clear way the method of frequency analysis into the cryptanalysis of simple substitutions. Well, of course, only a very simple kind of cipher, but very appropriate. And he explains in very clear terms how to proceed in practice with this method. So here is the al-Kindī tree. This is a classification of the various methods used at his time in a tree-like fashion. It's a very modern concept to present things in trees. This is sort of more computer sciencey than classical. And now, if you can't read this, don't worry, I can't either. Fortunately, the Mrayati et al. Made a translation of the tree into something better readable, but this shows you in a clearer way how these handmade trees and branches are meant. So you see very clearly the structure there. And here's the second picture image in a little bit larger, so you can see how he has this tree where he talks about two successive encipherments, super encipherment, or a simple, just one method for enciphering, and so on, and where letters retain their form, that is transpositions, and letters change their forms when you have substitutions. You substitute one character for a letter. And all this is very clear, and you could almost use this in a modern book on classical cryptography. So the main method used at his times and much later, and it's still in use by private persons today, are simple substitutions, where you simply replace each letter of the alphabet by some other letter. And a well-known example is Caesar's cipher, where you replace each letter by the letter 3 ahead in the alphabet. So instead of A, you write a D. Instead of B, you write an E. And actually, if someone knows a little bit about these ciphers, you can almost read down a text like this, and certainly with a little bit of care, it's trivial to decrypt this. But for most people, in any case, even writing and reading was a cryptographic problem. They couldn't write, they couldn't read. So this works for them at that time. And the most impressive achievement of al-Kindī, in my view, is a clear description of frequency analysis of such systems. So what he does, I mean, he proceeds just like one would do today. He sets up a frequency table of letters for Arabic, and he uses a fairly, a moderately sized database of 3,500 letters, which is okay, not too big, not too small. Then he writes, this is a modern form of a table which you actually find in al-Kindī's book. So a very careful presentation of the various letters. They are ordered by frequency here, and then there is the number of times they occur and the percentage. And for example, it's not a surprise that alif and lam are the two most frequent letters, because they already occur in the definite article, which is the most frequent piece in Arabic writing. And he goes on to analyze the ciphertext by checking the frequency of symbols in the ciphertext against the general table of Arabic, which he determined. And if you have ever tried anything like that, then you will know, well, if your ciphertext is long enough, then there will be a reasonable match, but there will never be a one-on-one match. Number one here is number one there, number two. That practically never occurs. But you try to match them up with the sample frequencies as well as you can. And concerning this, there is a well-known concept called the unicity distance, devised by the American engineer and mathematician Claude Shannon, who said that he's the founder of information theoretic security. And one of his findings was this, the existence of such a notion like unicity distance, which says if you want a unique decryption, deciphering of a message, it has to be at least so and so long. It's clear if I write just 4 letters, it's a simple substitution. There's no way to decrypt this, because any word in your language that has 4 different letters will match. And there's no way of telling which is the correct one. But there is a certain a minimal length depending on the entropy of the languages and the keys that you use. And al-Kindī, of course, he doesn't know about entropy. That's a very modern notion, but he is well aware of a qualitative version of this unicity distance. Namely, he says explicitly the statistics can only be expected to work when the given clear ciphertext is actually long enough. So here I've taken the liberty of transcribing more or less literally part of what he writes. That's not my, this is Murayati's translation. I'll more or less read it to you. One way to solve an encrypted message, if we know its language, is to find a text of the same language long enough to fill a sheet or so, and then we count each letter of it. We call the most frequently occurring letter the first, and next most the second, and so on. And then we look at the cryptogram we want to solve and also classify its symbols. We find the most frequently occurring symbol and change it to the form of the first letter, and so on, until we have accounted for all symbols in the cryptogram. But then it can happen that the cryptogram is too short to have all different letters. The more important thing is the high and low frequencies will not be correct, because they are only correct in long enough messages that correspond to all places of frequent and rare occurrences. So they will not be matching exactly, so equivalence does not apply. Then a second trick must be used to recover letters. And that is what one would recommend today also. And the second trick is the study of not single letters, but pairs of letters, digrams, or triples of letters, trigrams, and so on. And time is too short to mention more about al-Kindī's work, but it is certainly a great, an absolute breakthrough, establishing a new way of thinking about security in his sense, and which today we call cryptology. And also in terms of statistics and computational linguistics, these are all first achievements. Now, one will ask, did al-Kindī's work come out of the blue? Did he invent his cryptological methods by himself? And there's no definite answer to this, but very little remain of predecessors, if there are any. And the one who is the closest suspect is the linguist al-Khalil, who lived just half a century before al-Kindī. And he is another, he wrote a book on cryptography, Kitab al-Mu'amah, the book on cryptography. But that is lost. We only know about that book through references in other books, later books that have survived. And the Arabic poetry is a very highly developed art in itself, and he worked on understanding this, describing the patterns required in a precise way. He set up the first Arabic dictionary. He worked in combinatorics, again another first. Nobody thought about combinatorial questions at that time outside of Baghdad. And for example, how many words can you form with 2 letters, with 3 letters, and so on. And this is a typical Arabic question, because in Arabic you have the roots, typically 3 consonants of a word, kalama, to write, and then you form from this one source, you form many other words, by according to certain rules. And Khalil asked himself, well, what if I change, just given these 3 letters, how many words can I form? So, and he comes up with a correct answer, what is it, 3 factorial, 6. And it's assumed that his ideas influenced al-Kindī. And this is what I want to say about Arab cryptography, and there's another aspect I want to talk about, and that is Arab mathematics. And actually, all my life I've been working in sort of hardcore mathematics and computer science and cryptography, cryptology, but already in my student days, I was always interested in the history. What lay in the past? On what grounds are we building the things that we're building right now? And so I've always inquired and tried to learn about what happened in the past. And one of the shining lights for me, sort of one of my heroes, is a Muslim scientist. Oh, this is al-Khalil. I forgot this. So al-Khalil, he decrypted a message within a month, and it is clear that when you analyze this sentence of Khalil's, then you realize he did not know the methods that al-Kindī was about to invent just a little bit later, because with al-Kindī's method, you don't need a month's time to solve a message. So then there is another much later cryptographer called Ibn Abdurrahim, and he made clear what transposition ciphers are, and he talked about steganography, like hiding messages in an innocuous looking text. So I tried to make up an example like this phrase, secrecy through key ciphers, with protection. And as you can see, it contains the word crypto as the third letter of each word. Now, whenever you try to do this, I encourage you to try to make up some message by yourself. It's very hard to do this in a convincing way. So the mathematician is al-Khwarizmi, so he lived at this roughly the same time as al-Kindī, a little bit before al-Kindī, and he worked at the Bayt al-Ḥikmāh in Baghdad as well, and he wrote a book that sort of founded at least modern algebra, founded modern algebra in a sense. The Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, a fat book on computing by breaking and arranging. Al-Jabr means to break, and Muqabala is the other word. And what he did in that work is he introduced general techniques for solving linear equations, and that by breaking and rearranging, moving terms around equations, and he solved quadratic equations by completing the square. And two major fields of modern mathematics and computer science owe their name to al-Khwarizmi's work. Algorithm is a corruption of al-Khwarizmi's name, but it's derived from that. And in fact, in older English books, algorithm is spelled with an S instead of a TH. So to me, algorithm, I always thought it was a Greek word. It looks a little bit like Greek. It's an anagram of logarithm, but it's not. It's an Arabic word. And algebra, well, there you sort of see that it is likely to be an Arabic word, and that is from the breaking in his book title. Now, what happens is that at that time, there was, I will show you an example or two of what he did. And today, it looks like trivial. Why is he doing, you would ask yourselves, why is al-Khwarizmi doing something so complicated when it can also be done easily? Is this science? Well, it is great science because it's due to people like al-Khwarizmi that we now find the things trivial, almost trivial, that he was the first to show. And his problem, well, from our point of view, was that at that time there was no proper language to talk about equations. When I say linear equations, well, most people here in the room will think about ax plus b equals 0 or something like that. You will know what I'm talking about, and I don't have to say much. And when I say ax plus b equals 0, then you know exactly what I mean. And al-Khwarizmi at his time, there was no such language, and it was very hard for him to express anything like that in the existing language. And the language that we use today was only basically introduced by Viet and in the 16th century. Al-Khwarizmi was actually not an Arab. He was probably of a Persian origin, and he came from Khwarizm, and this is in the border area between Uzbekistan in the north and Turkmenistan in the south. So and today Konya-Urgench or the old Urgench, traditionally called Khwarezm or Khwarazm, and here you see very clearly how his name derives from that location. that lies today in Turkmenistan, and quite close, maybe 30 and 50 kilometers away, are Urgench and Khiva today in Uzbekistan. And this is a Soviet stamp recalling Muhammad al-Khwarizmi. Here is the kitab, a luxury edition, not the Penguin, a paperback edition, the luxury edition of the Kitab al-Jabr of the book of al-Khwarizmi. And this is a statue of al-Khwarizmi, a radiant picture in the early morning sun, just a beautiful, you see how self-contained, self-assured this man looks, really relaxed and calm. This is the statue in its full beauty in Urgench. And this is another statue of al-Khwarizmi in Khiva. Visually not that as is attractive, I find. And this is the same statue as just before. And no, he's not speaking into his mobile phone, but he's reading the scroll that lies in front of him. And this is one of the many mosques, minarets in Khiva. And here is the title of his book. And this is a little bit enlarged. So this is a bronze monument. Yes.
He's reading upside down.
No. What?
Al-Khwarizmi is reading upside down, even where he's standing.
I write a modern version of this text down here. Oh.
It's writing upside down, right? Because the text is written so that we can read it. Am I wrong?
Yes, unfortunately. This says the same thing. Hisab, al-Jabr, wal Muqabala. I don't know what you mean, and he's upside. He's sitting like that, and do you think he's not speaking into his phone?
I think he's not reading the parchment because it's turned toward us, not him. Yeah.
There you have a point, but okay. I didn't look at the upside of the parchment. You're right. Possible explanation, I'll try to wiggle out of this, is that this is a geometric diagram, and there may be more geometric diagrams up there, and he may be studying them. But you're right, and I see your criticism. Yeah. Huh?
Was it you who took the picture?
I took the picture. Yeah, I took all the pictures of al-Khwarizmi. Yeah, I made 2 pilgrimages to the places of al-Khwarizmi. So that's again so an overview of al-Khwarizmi's work is that he contributed substantially to astronomy, to geography, and making maps, map making. Probably his easiest but most important contribution was to pass on the decimal notation invented in India. It just before, without the decimal notation, like in the classical Roman notation, the Roman numerals and so on. My personal conjecture is, why did the Romans not produce great mathematics? It's not for lack of mathematical talent, but it's just because they spent all that talent on adding and multiplying numbers. You know, when it's so hard to manipulate numbers, then going beyond the trivial things like simple calculations requires just too much energy, and you get too absorbed, the detail, you get bogged down in difficulties. And it may be that the notation of numerals in Roman times hindered that. But now with the decimal notation, and actually the other bases are just as well. The hexadecimal notation in Mesopotamia, which we still have in our clocks, 60 minutes to an hour, and also a duodecimal notation. In computing, we have a binary notation. All these positional notations are equivalent in a sense. They're easy to manipulate, and but we have the decimal notation. And Al-Khwarizmi's book was translated into Latin starting in the 12th century on. There was an intellectual, one of the very, very few German intellectual emperors was emperor, had his residence in the southern part of Germany. It's today called Sicily, and he had great contact to Baghdad, to Arab scientists, and he had these books translated. Now, I'll explain, if you have the patience, his example for solving a quadratic equation, and you will be, if you remember the method you might have seen in high school for solving quadratic equations, you will sort of recognize it. And if you don't, then I suggest you take a nap right now, because it will get a little bit boring if you don't follow the math. So the one thing that makes all of Al-Khwarizmi's texts very loquacious is that, for example, he has no notation for an unknown or root or solution, like where we use X's typically or other letters, and he just has the word shay, which means thing. And here's an example. This is the last piece of my talk. This is one quadratic equation. So Al-Khwarizmi starts with a challenge. You divide 10 into 2 parts, multiply the one by itself, it will be equal to the other taken 81 times. Now, first thing you have to do is you have to translate that into our usual language. And at times there seem to be several options, but it's clear here that this is the correct translation. So the one thing is 10 minus x, and the other thing, the other part is x. Now you say 10 less a thing multiplied by itself is 100 plus a square less 20 things, and this is equal to 81 things. So he multiplies out 10 minus x squared. You know the binomial formula. It gives you this, and I don't know why I wrote it this way. And here is the 81x. Now, I wrote the 20x at the end here. It's really the middle term. He says to separate the 20 things from 100 and a square. So you separate this expression from the other expression here. And that is, you add on both sides 20x. Okay? One of the obstacles for al-Khwarizmi and for a long time also in the early Western science was that negative numbers were not really recognized as numbers. You know, the people were uncomfortable with them. So this is a legitimate equation because only positive terms occur, and the negative parts you always have to bring to another side. And, you know, in some sense, the same occurred around 1800 when Gauss invented the complex numbers, and many people at that time felt very uncomfortable. They weren't accepted. In fact, they were, part of them was called imaginary numbers because they were not real numbers. And so you do this, you carry the 20x to the other side, you get the equation below. And I repeated that, and I can rewrite it in this form. And now you have the roots. It's not so clear what it wasn't clear to me, at least when I read this, what this exactly means. Because x is the root, but you don't have x, but you have the linear coefficient 101 here. And then you get what we now call the quadratic complement, namely half of 101. And so I've written this out here, that you complete the square, then you get this squared, well, that's this squared, and you multiply that out, and the first two terms here agree with the first two terms there. That's the goal. Finding the right quadratic complement achieves this, or is defined by this goal. And now you have this sort of unwanted extra term. You compute it, so you multiply it by itself, and then you get 2,550 and a quarter, whatever that is. And then you subtract this from 100. This is the 100 here. You now have to subtract this because you want to have an expression, this equals something, and then you have to get, but this is the equation you have, so you have to add 100 and subtract this. And then you get this 2,450 and a quarter. And now comes the typical textbook miracle. You take the square root of that number, and it comes out to be 49.5. Now, this only happens in textbooks for schools, that the square root that you have to extract during this method actually happens to be a very simple number, a rational number in this case. You know, most square roots are more difficult to describe. Okay, and then you subtract this from the quadratic complement, which is 50.5, and there remains 1, and this is one of the two parts. So 50.5 minus 49.5 is given here. The rule is equal to 1, and then I did the check. Al-Khwarizmi doesn't say, it doesn't do a check, but you may have learned that it's wise to do this kind of check at the end, and if you plug 1 for x into this equation, then it becomes true. And there's another solution, of course. As you know, quadratic equations always have two solutions, except that when by coincidence they coincide. And the other one is 100, but that doesn't make sense in al-Khwarizmi's world, because you cannot subtract 100 from 10. doesn't work. And this finishes my talk. I just want to list some open questions. What I find the most interesting question is whether some of these lost books of Arab cryptology have survived. That's the most interesting question. And another one is, are there any actual examples, say, of diplomatic correspondence where cryptography, encryption was actually used? I'm sure they are, and they will be hidden. They will be hidden somewhere in the archives, but there are many archives, and this is a searching for these for such documents requires you to have a basic understanding of cryptography, but not very much. This is very simple cryptographic stuff, but you must be able to read old handwritten Arabic, and there are very few people in the world who have both qualifications. If you're looking to become famous, this is the way to start. Go into the dust, breathe the dust of the old archives, and go look for such documents. So the conclusion is that in Arab cryptology, you have a rich past that people can be proud of, and you have current efforts like the TII, and I can only add my best wishes to that. Thank you. Shukran.
Obviously, we are very late, but we have time for questions. Yes.
So you mentioned, so my understanding was that algebra meant collection, and it comes from the fact that in algebra you convert terms, and that's what his technique that you described.
No,
but you gave a different interpretation.
No, jabr means to break, and muqabala is more the collection.
So what's the meaning there of to break? What's the meaning in the title then?
Breaking and rearranging terms is the usual translation. There is no, these terms don't have literal, have disputed translation, if you want, like many terms in Arabic, but I think breaking and rearranging is a good translation.
So in the beginning, first of all, thank you for your talk. I think this is something that many of us are not aware of. At the beginning of your slide, you mentioned the Arabic word simple, which means zero in English. And this word is associated with the word cipher in English. And I saw this argument within the book of David Kahn. So I read the book and I saw that he mentioned this, but he doesn't mention the reference where and how such association was introduced, like associating the word simple in Arabic and the word cipher in English. So then when I came to UAE, this is an Arabic-speaking country, I was expecting that the word simple to be used in the Arabic name for cryptography. So, but when I came here, I realized that they actually make the word shafar in Arabic. So the more Arabic words for cryptography is ulum tashfir. So they didn't, so the Arabic didn't use ulum tashfir, which would translate means as knowledge of zeroization. But the Arabic words for cryptography is ulum tashfir. And tashfir is a different word.
So that has a sheen in it, not a sad.
Exactly, not a sad. The actual words for cryptography that is usually not. So my question is, like, are you aware of a reference older than David Kahn that maybe explain the argument behind the association of the word cipher and ciphering?
No, I've never thought about this. First of all, thank you for pointing out that cipher in the sense in the sense is not used in cryptological terms. I understand that mu'ammar is a common term, but mu'ammar.
But the more
Yeah, I have no idea. I can only thank you for pointing this out. All I can think of right now is sort of a funny thing. There is a I read somewhere an English poem where a poem in English where almost all words, not all, but almost all words are cipher. CIPHER. And it starts, I don't remember exactly, I sigh for you, you sigh for me, and so on. So all our sighing, no, I don't remember exactly how it goes, but I know that to sigh in the sense of breathing heavily is used facetiously in that sense. But that is not a serious answer to your question, and I wouldn't know where to look for the origin of that.
Yeah.
Huh?
I have a guess on where it comes from.
Huh?
My guess is that it comes through French from Italian. In Italian, cifra means digit or symbol, which is more easy to associate with zero. And in French, it means the same, chiffre. And cifrario, cifratura, is the art of translating symbols to other symbols. So that's my guess. I have no text to give you as a quote, but that's the quote.
I guess also about what Jean-Paul just asked about the debit. I don't know if maybe understand this. Doesn't it mean see? You know what seeding? Like seeding. Like you would say for the if I go to my error, for example, sometimes they that is not isn't related to seeding.
see,
I think because we know that I'm from Senegal and we use a lot of words from Arabic, and we have it's like very similar word to Jabra, and it means see, exactly see. And I'm just like thinking maybe Jabra is like the maybe ancient Arabic is very related to that sealing, and that sealing means just like you just like breaking stuff. Make them smaller and so that you can find.
Yeah. So, but you first break stones, and then you sieve out the small pieces, like.
That's my thing.
Yeah, I don't know.
We have a comment here. Work in the group online. It says, "Sir, sorry for a superficial question. Jabber, in my understanding of Arabic, is the main repair, not to break."
Yes, it's okay. I really don't have an answer to that. You see, I'm not a native Arab speaker by far. I mean, I'm not even an Arab speaker really. So all I can repeat is what I learned about the word jabr, and that is that it means to, jabara means to break, but maybe not. But we have some native speakers here. So jabara, does that mean to break? Jabara. The verb behind al-jabr. Hmm? Okay. Okay. Yeah, I'm learning something new here. Thank you. I don't know what to say to that. That's beyond my. Any more questions? Yes.
I have one. As mathematicians, we usually do a very bad job of keeping context. Do you have any idea why Al-Khwarizmi was interested in solving quadratic equations? As he explains why.
Well, what would you do if you have provided a complete solution for linear equations, and now we're looking for another outlet for your great ideas? It's sort of the natural, the easiest generalization, the next general question, I don't know the reason, but certainly Al-Khwarizmi was familiar with quadratic equations per se through the Greek works. There are many Greek works dealing with conic sections and so on, where quadratic equations occur all the time. And so he was well aware of what a quadratic equation looks like, and that it is not as easily solvable as a linear equation. But then he probably came up by himself, but maybe learned it from some Greek source, I don't know, how to do this. And so he then made up these examples. These examples are clearly cooked for the textbook.